Technical processes can be roughly divided into industrial processes and discrete parts manufacturing. In industrial processes, liquid, solid, or gaseous materials are produced by biological, chemical, or physical processes. Serious danger is often involved in industrial processes, such as the risk of explosion or contact with poisonous substances. Safety is therefore a major aspect in the automation of such processes. Generally, an industrial process must not be interrupted, and it is often difficult to predict exactly how long it will take to produce the product. Discrete parts manufacturing creates production lots of a product, such as screws or automobile bodies or bottle filling. They are normally mechanical processes. The main emphasis here is on throughput and speed. Both types of process can be further divided into the categories manufacturing processes, distribution processes, and storage processes. Processing in industrial processes includes, for example, chemical reactors, as used in the chemical or pharmaceutical industries. Processing in discrete parts manufacturing can be found, for example, in turning shops or in rolling mills. Distribution in industrial processes typically makes use of tankers or pipelines. In discrete parts manufacturing, distribution might involve assembly lines and packing machines. Storage in industrial processes includes, for example, tank farms or silos. In discrete parts manufacturing, for example, high-rack warehouses. Within industrial processes, a distinction is made between continuous processes and batch processes. Some of the feature differences can be illustrated using an example. A vaporizer is an example of a continuous process. A group of stir tanks is an example of a batch process. A continuous process produces large amounts of a product in a continuous product flow. The longer the process runs, the more product is produced. A batch process, on the other hand, normally produces comparatively small amounts of a product in a discontinuous process. A continuous process produces only one product. A batch process is often used to create several different products. As a basic principle, we can say that the main aim of a continuous process is to maintain a steady operating state in each unit involved in producing the product. While in batch processes, various different states may be required at different times in a unit to produce a product. For example, heating, stirring, and cooling are process actions that may be accomplished in the same unit during a batch. In a continuous process, the know-how is in the process controls and in the resulting automation solution, while in a batch process, the recipe contains the essential know-how for producing the product. At this point, we have seen that industrial processes can be classified as continuous and batch processes, and we have looked at the major differences between them. If a batch process needs to be automated, the first question that arises is whether or not the use of a batch system will be beneficial. Based on the following 6 criteria, we can find the answer to this question simply and objectively. The use of a batch system is indicated when the same set of batch equipment is used to produce many products. When production activities are often extended by adding new products or replacing old products. When production activities are frequently being optimized. When production activities and all the variables influencing the product need to be logged. When it is necessary for operating personnel to be able to create or modify production activities. When it is necessary to be able to dynamically allocate equipment to a batch. The more criteria met, the more likely that a batch system will be the best choice. Batch management software is frequently found in manufacturing, biotechnology products, pharmaceuticals, paints and varnishes, fertilizers and pesticides, food and drinks, detergents and cleaning agents, plastics and adhesives, chemicals and mineral fibers. An example taken from everyday life of a batch process is the process cell we know as the kitchen. We all have first-hand experience of the activities and production procedures here. If we have a brief look at what goes on in the kitchen based on the criteria discussed in Applications and Branches, we can decide whether continuous or batch processes are involved. The production process is described using recipes. The chef can introduce new products or modify existing products at any time. More to the point, the chef can do this without the aid of the kitchen manufacturer or the team that installed the kitchen. Recipes are continuously optimized. In some situations, it may be necessary to document certain activities for the health authorities, for example, changing the oil in the deep fryer. When boiling water is required in a certain step, a wide variety of pots, in other words, units, can be used. While the water for the spaghetti product is being heated in a pot, it is, of course, also possible to peel the fruit for the fruit salad dessert. Several products are being produced in the process cell at the same time. The kitchen production cell obviously meets all the criteria we mentioned earlier, and is a classic example of a batch process cell. For this reason, and because you know precisely what happens in a kitchen, we have chosen this as the production cell for the example that will introduce you to the capabilities of SIMATIC batch. Let's have a closer look at exactly what happens in a restaurant kitchen. What is the working environment of the chef? The chef has recipes that not only specify how to make a dish, but also include the ingredients and the necessary amounts. Within the batch context, these recipes are known as master recipes. Several cookers, hot plates, and pots are available with which the dish can be prepared. Within the batch context, each cooker, hot plate, and pot is known as a unit. The set of cookers, hot plates, and pots in this kitchen is the process cell. The tendency today is to order the required material for an industrial process cell using tools from the Manufacturing Execution System, or MES level, or Enterprise Resource Planning, or ERP level. To avoid making the example too complicated, we will simply assume that the required material is available. When a customer orders a meal, the waiter creates a production order to trigger production. Once this production order reaches the kitchen, the chef begins to implement the order. Normally, the preparation runs parallel to other orders. Some of the existing pots, hot plates, and cookers will probably already be allocated for other orders. As a result, the chef has to select free resources or units, or wait until a specific resource becomes available. Once the chef selects his equipment, he follows the recipe to produce the finished product, the meal. The advantage of working with normal colloquial terminology is that no new terms need to be learned and understood. However, the danger is that some terms may mean different things to different people. A chemist might understand a recipe to be the chemical composition, whereas the system engineer considers it to be a sequence of steps. Within a process engineering environment, it is therefore important that everybody speaks the same language and uses the same terminology. With this in mind, a basis for terminology was provided by NAMUR, the User Association for Process Control in the Chemical and Pharmaceutical Industries, with NE 33. The ISA did much the same with the ISA 88 batch standard. Important terms, for example, include master recipe, control recipe, batch, and process. ISA 88 corresponds to the older ISA S88, whose name was changed. Where ISA S88 is mentioned, ISA 88 is always meant. A master recipe contains the instructions for manufacturing a product with all its input and output materials. A master recipe can either identify specific units to be used in producing the product or specific unit classes, from which a unit, when needed, can be selected manually by the operator or automatically by the batch manager. A control recipe is a copy of the master recipe, where additional information specific to the batch has been added. A batch is the amount of a product to be made with specified equipment within a defined production run. The production run itself is also called a batch. A recipe procedure describes the unique sequence of chemical, physical, or biological activities required to produce a product. A master recipe is comprised of several components: a header, a procedure, a formula, and an equipment requirement. The recipe header contains general information about the product. Since uniform terminology is important, we will briefly align the language of the chef with that of ISA 88. For the chef, spaghetti bolognese is a dish. For ISA 88, it is a product name. The chef calls the standard amount for which the recipe is intended something like number of persons. In ISA 88, it is called reference scale. The chef would call minced meat, mushrooms, and pasta ingredients. ISA 88 calls them input materials. A recipe procedure is comprised of one or more unit recipes that can, in turn, consist of several recipe operations. The cooking instructions in our example can be mapped to the recipe procedure. The first part of the cooking instructions, make bolognese, consists of 5 substeps. The first 3 substeps cover the preparation of the dish, and in unit recipe 1 are mapped to the recipe operation called preparation. Warming up the pan is mapped to the heat recipe operation of unit recipe 1, and the 5th substep to the simmer recipe operation of unit recipe 1. The instructions 2 through 4 are mapped to unit recipes 2, 3, and 4. At this point, the actual pan or pot that will be used in making the bolognese dish has not been specified. In other words, which unit will be used for production is still unknown. The master recipe is therefore still neutral in terms of equipment and allows flexible planning of the necessary production facilities. The ability to formulate master recipes without stipulating the specific equipment means a considerable cost savings in both master recipe creation and maintenance. One important criterion in the classification of batch process cells is whether or not different products can be created in the same process cell. A second important criterion is whether one or more production lines are available to produce the product or products. If there is only one production line and one product, this is known as a single line, single product process cell. If several production lines are available to produce a product, this is known as a multiple line, single product process cell. If several products are produced in a process cell, this is known as a single line, multiple product or multiple line, multiple product process cell, depending on the production lines available. This next section describes the ISA 88 physical model. At the top level of this model there is the enterprise. We've chosen the international enterprise called Pizza Top so that we can keep to our example of the kitchen. The company has a large number of branches or factories that ISA 88 would call a site. For example, Germany can be called a site. The US could be another site. A site can consist of several plant areas. In our example, an area can be the storefronts for Pizza Top in Karlsruhe, Germany. Each area or city, in turn, can contain one or more storefronts, each called a process cell, in which one or more products can be produced. The highest relevant product-producing hierarchy level of the physical model of ISA 88 is the process cell. The levels above this level represent business entities and have no effect on the actual product production. A process cell consists of all the equipment required to produce one or more products. In a real project, it can consist, for example, of a reactor and all the valves and pumps in the inlet and outlet pipes, as well as the buffer storage before or after the reactor. In our example, the process cell is a storefront or a kitchen. In the physical model of ISA 88, a process cell is further divided into units. In practice, a unit can consist of the reactor and all the valves and pumps in the inlet and outlet pipes mentioned earlier. The buffer storage facilities mentioned earlier are also units. In our kitchen example, a unit may be of an oven, a pot, or a hot plate. In ISA 88, the levels below units are defined as the equipment module level and the control module level. An equipment module can consist of one or more control modules. Examples of control modules include a temperature sensor, a control valve, or a pump. The control module level is transparent to the batch system. This level is generally completely controlled by the automation system and is addressed by batch through the use of equipment modules. In our kitchen, the equipment module may be the chef setting the oven temperature. Once the temperature is set, the oven takes over and controls the oven at the set point without further intervention from the chef. The physical model of ISA 88 and the structural elements it defines, the process cell, unit, equipment module, and control module, provides a method of structuring the physical equipment in a process. The second model of ISA 88 that you will get to know here is the procedural model. This hierarchical model allows you to organize the steps needed to produce a product. The top hierarchy level in a recipe procedure is called the recipe procedure. A recipe procedure runs on a process cell and describes the entire strategy used to produce a batch of a product. The recipe procedure is comprised of an ordered set of recipe unit procedures. A recipe unit procedure runs on a unit and implements a process stage. At any one time, a unit can only be allocated to one batch. A recipe unit procedure, in turn, consists of an ordered set of recipe operations, known as ROPs. Recipe operations also run on units. A recipe operation normally describes a chemical or physical conversion of the materials of a batch. The lowest hierarchy level is the recipe phase. A recipe operation consists of an ordered set of recipe phases and handles a process action. The instructions for preparing the spaghetti in our kitchen example might be as follows. The produce spaghetti instructions are mapped to the recipe procedure. The instructions for cooking the pasta or preparing the sauce are each mapped to a unit procedure, since these activities take place in different units. The steps involved in cooking the pasta, such as filling with water and adding salt and oil, are formulated in the preparation recipe operation. The steps required for filling water, heating, and stirring are implemented with the recipe phases of the preparation ROP. You now have an understanding of the physical and procedural models of ISA 88. We have also presented one possible way in which our kitchen example can be structured. We will now move on to describing the integration of these two models in a SIMATIC PCS 7 somatic batch solution. These models are used to structure plants and process cells in SIMATIC PCS 7 and somatic batch. Where will you find these two models? To answer this question, let's look at a unit. The physical mapping of a process cell with its units can be done in either the plant hierarchy view or in the process object view of SIMATIC Manager. Among other things, SIMATIC Manager is used to manage all the charts and sequences used to program the automation stations. All the objects relevant to SIMATIC Batch are indicated in green and are available to SIMATIC Batch. Batch configuration data does not need to be entered a second time in SIMATIC Batch, eliminating a potential source of error as well as reducing the engineering effort and costs for creating and maintaining a batch application. The recipe procedures and underlying unit recipes, recipe operations, and recipe phases are formulated in SIMATIC Batch. In other words, the procedural model of ISA 88 is implemented in SIMATIC Batch. How can we now structure our kitchen example in the SIMATIC Manager and in SIMATIC Batch following the ISA 88 concepts that we just spoke about? Let's first look at the physical model and SIMATIC Manager. The kitchen is the process cell. The oven, pans, and pots are units. These units will be grouped into process classes. Functions such as turning or stirring are equipment modules. As already mentioned, control modules are transparent to the batch system and are addressed at runtime through the equipment modules. Let's now look at the recipes that will run in the identified equipment. The ISA 88 recipe model is fully supported in SIMATIC Batch. Recipes are created using the SIMATIC Batch recipe editor. Using this editor, you create a recipe procedure. Recipe unit procedures are then defined and assigned to the recipe procedure. Each recipe unit procedure can be assigned one or more process classes. At this point, you can either assign a specific unit to be used when this recipe unit procedure is run, or you can allow the batch manager to dynamically select an appropriate unit at the time the recipe unit procedure is to begin running. In the kitchen example, specific units can be assigned to each recipe unit procedure. Desk 1, Pan and Pot 1. Recipe operations are assigned to a recipe unit procedure by creating them in the column representing the recipe unit procedure. The synchronization of recipe operations in different units is achieved using synchronization lines. Recipe phases are the building blocks for a recipe operation. You will find detailed information on the use of phases in SIMATIC Batch in the section First Steps in SIMATIC Batch on this DVD. SIMATIC Batch version 6.0 was released along with the SIMATIC PCS 7 process control system in the spring of 2003, following a phase of intensive field trials. The knowledge and experience gained during these trials was included in version 6 and is now available to the user. Before we look at some typical system configurations, we would like to introduce you briefly to the essential components of SIMATIC Batch. The Batch Engineering software provides you with the easy-to-use tools to configure the process model and sequences used by SIMATIC Batch. This software is available on the SIMATIC PCS 7 installation CD. There is no license needed to run this software. It is an integral part of the SIMATIC Manager engineering tool. It is available on every engineering station. The Batch Control Center, or Batch CC, is the command center. It provides you with the tools to configure recipes, plan batches, and monitor and control SIMATIC batch processes. With Batch CC, you can manage all data relevant to SIMATIC Batch using a graphic user interface. Batch CC also allows you to graphically display unit allocation data. Batch CC is installed and operated on batch clients. The Recipe Editor provides a graphic user interface for simple, intuitive creation and modification of master recipes and library operations. Recipes are built using the recipe building blocks developed during the configuration of the process hierarchy in SIMATIC Manager. The Batch Recipe Editor can be started from the Microsoft Start button or from Batch CC. The Recipe Editor is installed and operated on the batch clients that you want to be able to use to create and administer recipes. The Batch Basic Package consists of 3 components: the Batch Server software, a Batch Control Center, and a recipe system. Additional Control Center and recipe system packages can be ordered individually. The server software is installed on the batch servers and supports up to 150 batch process objects, PO. Options and power packs are available to increase the PO support to 300, 600, 1800, or unlimited process objects. Within the context of SIMATIC Batch, a process object is an instance of a unit or an equipment module. Batch Planning is an option for Batch CC, allowing convenient graphical planning of batches. The Hierarchical Recipes optional package allows users to formulate hierarchical recipes as described in the ISA standard ISA 88. The option is installed on batch servers. Without this package, you can create flat recipes. In its most basic form, a master recipe is a combination of a recipe procedure and a recipe formula. If your process has master recipes that differ only in formula, SIMATIC Batch provides an option that enables you to link multiple recipe formulas to a single recipe procedure. With this option, changing the recipe procedure will automatically update all the master recipes linked to that recipe procedure. This option is installed on batch servers. User-created recipe operations, known simply as ROPs, can be administered conveniently in a user library or ROP library. These library recipe operations can be included in recipe procedures as references and can therefore be modified centrally. This reduces the effort for master recipe engineering and validation. The Application Programming Interface SIMATIC Batch API is an open interface for customized expansions. The SIMATIC Batch API provides the user with access to data and functions of SIMATIC Batch and allows specialized branch or project-specific applications to be programmed. The option is installed on batch servers. Last but not least, we come to the software components for access protection and permission management. SIMATIC Batch provides not only efficient and configurable access protection, but also precisely definable role management, with which functions can be enabled or disabled for specific operators. These functions are configured mainly in the Batch Control Center, using the SIMATIC Admin tool. The basic strategy is to assign certain roles defined in SIMATIC Batch to user groups created in Windows. All the users of a Windows group then automatically have the rights of the SIMATIC Batch role. User management is defined solely under Windows, using all the functions it makes available, such as expiry of a password after a certain time. Both workgroups and domains are supported. The admin tool must be installed on a SIMATIC station once per process cell, along with the BCC and the logon service. The logon service provides the functions for logging a user on and off. Once a user has logged on, their role and therefore their rights are automatically recognized in SIMATIC Batch. The logon service and the logon admin tool are not components specific to SIMATIC Batch, but are general SIMATIC components that can be used in SIMATIC Batch. The last component we would like to introduce is the electronic signature. This optional package enables the recipe developer to require certain operator actions or batch events to be signed off before the operator command is carried out or batch sequence is continued. For each operator action or batch event that requires a signature, it is possible to configure which signatures are necessary and whether signatures must be made in a particular order. The option is installed on batch clients. Now that you've got to know the key SIMATIC Batch software components, it is appropriate to look at some of the recommended batch application architectures. The specific architecture you implement for your process depends on your needs. In our examples, the automation system will have 3 automation stations. In some cases, these are redundant, along with devices and remote I/O stations connected to Profibus. The first example illustrates a small system with 1 engineering station and a single station on which both OS runtime and batch server and client functionality are installed. The PC should have at least 2 monitors, so that there is enough screen space to be able to control and monitor the Batch Control Center, Batch CC, and the OS at the same time. In the second example, 2 operators will control and monitor the system at the same time. The automation systems always have 1 engineering station connected at all times. A client-server architecture is installed for operator control and monitoring and for SIMATIC Batch. The ES server is connected to the automation stations over the system bus. There is also a terminal bus, over which the 2 clients are connected and at which the 2 operators work. The displayed process values, messages, and pictures come from the server. All operator input to the automation station is through the server. The engineering station is also connected to the terminal bus over which downloads are made to the clients and server. Let's now look to see where the SIMATIC Batch software components are installed in this architecture. The batch engineering software is installed on the engineering station. The server PC contains the batch server software for 150 process objects and the hierarchical recipes option. In the architecture, we also want to be able to create recipes on one of the clients. This means that the recipe editor is required on this client. We also want this operator to be able to control and monitor the running of the batch, so that a batch control center is also required here. A further batch CC is installed on the second client. Since the batches will be planned here, the batch planning option is also installed on this client. In the third example, 6 operators will control and monitor the system at the same time. The engineering station is once again connected to the automation stations over industrial Ethernet. Due to the more exacting requirements, the 2 OS servers are set up redundantly. Both pairs of servers are connected to the terminal bus. A redundant OS server setup requires separate batch servers that are also set up redundantly in this case. The combined OS and batch clients from the previous example are extended by 2 OS clients without batch and 2 batch clients without OS. The batch engineering software is once again installed on the engineering station. The 2 redundant batch server PCs both have the server software and the options Hierarchical Recipes, ROP Library, and the Separation of Procedure and Formula installed on them. The recipes will be created on Client 1. This, therefore, has the recipe editor and SIMATIC logon. However, it is without a batch control center. Clients 3 and 4 are simply OS clients for operator control and monitoring of part of a plant that is independent of SIMATIC batch. Batch planning and control will be handled on clients 2, 5, and 6. Here, in addition to the OS software and the batch control center, the batch planning option and SIMATIC logon are also installed. Since access protection and electronic signatures are also required, the admin tool is installed on Client 2. The fourth and last example is based on example 3. Due to the additional requirements for availability, redundant domain controllers will be used to provide user management. An additional PC with SIMATIC IT and a customized application will also be installed. These communicate with SIMATIC Batch using the Batch API. To support SIMATIC IT and the custom application, the Batch API is installed on the 2 batch servers. In the 4 examples shown, you have already seen one of the major advantages of SIMATIC Batch. With its modular design, SIMATIC Batch can be adapted easily to the customer requirements in terms of numbers of objects and functions. To conclude this section, we would like to draw your attention to other important highlights of SIMATIC Batch. The tight integration of SIMATIC Batch in PCS 7 makes repeated entry of configuration data during engineering unnecessary. The process model configured for use in the automation system is also used in SIMATIC Batch. Therefore, no additional equipment editor, as needed with some other batch systems, is required. It is also not necessary to program or configure interfaces between the batch system and the automation system. Modifications in the engineering system can be adopted with an update function in SIMATIC Batch. During operation, operator inputs and messages or alarms are automatically logged in the batch reports. Batch unit and phase faceplates are available as standard on the OS. SIMATIC Batch supports the formulation of equipment-independent recipes. SIMATIC Batch supports dynamic unit allocation. Units can be allocated based on a variety of strategies. The batch planner can assign a specific unit to use during batch planning. SIMATIC Batch can dynamically allocate a unit based on the process classes assigned to the recipe unit procedure. The recipe author can allocate the unit at the beginning of the batch or when the unit is needed at runtime. An external source, such as an MES system, can be used to allocate the unit. To increase availability, hot standby redundancy is available. With the recipe editor, SIMATIC Batch provides a convenient tool that you can work with simply and intuitively to graphically create and administer both flat and hierarchical recipes. With access protection, electronic signatures, and other functions, SIMATIC Batch meets the requirements of 21 CRF Part 11. SIMATIC Batch has an integrated planning system for batches. This allows the allocation of units and the timing of batches to be visualized in the form of Gantt diagrams. The Batch API optional package allows simple interfacing of applications from the manufacturing execution level, MES, with SIMATIC. SIMATIC Batch is a SIMATIC PCS 7 program package that can be used to automate batch processes of varying complexity. With SIMATIC Batch, master recipes can be created graphically, validated, and released to production. Based on these master recipes, batches can be planned and started on an OS or SIMATIC Batch client. The main features of SIMATIC Batch are simple graphic recipe creation, user access permission management with precisely definable access rights, comprehensive logging of all events for production verification, simple and clear batch planning that can be interfaced to higher-level product planning and control systems, and modular and scalable solution structure. SIMATIC Batch is made up of various components: the Batch Control Center, also known as Batch CC, the Recipe Editor, the Batch Control Server, the Batch Report, and the interface blocks. The Batch Control Center is the central component in SIMATIC Batch for batch planning and batch control. The Batch Control Center is used to read in the process cell data of the basic control, specify user rights for all SIMATIC Batch functions, define the input materials used and the end products and byproducts produced in the process, and create and maintain master recipes and libraries. Production orders can also be managed here if no supervisory system from the manufacturing execution level is used. The Batch Control Center can also be used to start, monitor, and control batches. The Batch Recipe Editor provides a graphic user interface for creating and administering master recipes and library operations. The basis for recipe creation includes, among other things, the units and equipment phases that are defined in the SIMATIC PCS 7 engineering system. The Batch Control Server controls and monitors the sequence of the current batches, while at the same time communicating with the automation systems via the OS. Since all the operator input is made from a batch client, the Batch Control Server does not have its own user interface. Nevertheless, a client can be installed on the same PC as the server. The batch data, online data, of SIMATIC Batch is stored temporarily in the SIMATIC Batch Online Data Management module. The Batch Report module documents the recipes and batch data in the form of reports. The off-the-shelf recipe report contains all the data required for and relevant to producing a batch. This includes information on the master recipe assigned to the batch, the input and output materials used in the batch, the recipe procedure executed during the batch, any fault and error messages, and any operator intervention. The batch report contains all the information required to reproduce the batch process for reasons such as quality assurance and fulfillment of legal requirements. SFC types and special interface blocks can be used for communication between SIMATIC Batch and the automation stations. These are supplied with SIMATIC Batch as a block library. Following installation of the library, the blocks are available for use in the engineering system. The following is an overview of the basic functions of SIMATIC Batch. Starting with the PCS 7 project, you will see all the steps leading to a running batch. You can try out most of the steps shown here by working through the document Part 2, Quick Start of SIMATIC Batch Getting Started. First, we would like to provide you with a brief overview of the project. Apart from the normal raw materials and ingredients, the kitchen project has 4 unit classes with units assigned to each: a desk, a pan, 3 pots, an oven. All the actual units belong to corresponding unit classes. The desk unit has the following processing capabilities, represented by equipment phases: drain, fill solid, and turn. Some of the other units have the same processing capabilities as well as other processing capabilities. These processing capabilities, too, are represented by equipment phases. In addition to drain and fill solid, these additional phases are temp, add ingredient, and stir. The pan unit class also includes the turn equipment phase. Based on the drain equipment module of the pan unit class, we will now show you how an equipment module is used in the engineering system. The project is opened in the SIMATIC Manager. As you saw in the first part, equipment modules are displayed in the plant hierarchy. The drain folder contains a CFC chart called Pan Drain. This CFC contains an instance of the Pan Drain SFC type and a simulation block. The instance of an SFC type is handled like a normal block in CFC and can be used directly in SIMATIC Batch as a recipe phase in a master recipe without any further engineering. The SFC editor is opened by double-clicking on any free point in the block. Since an SFC type can be instantiated more than once, and each instance linked to the blocks of the equipment module, the instructions in the steps and the conditions in the transitions are formulated using the input and output parameters of the interface of the SFC chart. The I/O parameters are displayed in the CFC editor as inputs and outputs of the block that represents the instance of the SFC type. The last part of this video describes how to create an equipment phase. You are now familiar with the key components of SIMATIC Batch and have already had an overview of the sample project. In the next section, you will see how SIMATIC Batch is integrated into the SIMATIC PCS 7 engineering system. The sample project ZEN3301, that is also on the CD as a backup, was adapted to the client-server architecture and was renamed ZEN3301VS. The OS client and OS server are loaded and started. The SIMATIC Batch applications are created in the PC stations. The first step involves specifying the types of the objects relevant to SIMATIC Batch in the SIMATIC Manager. This is done in the Properties dialog of each batch object. First, the Kitchen folder is marked as a process cell. The Kitchen folder is now shown in green to indicate it is a SIMATIC Batch batch object. Before the existing units can be assigned to unit classes, the unit classes must be defined. The unit classes oven, desk, pan, and pot need to be defined. The necessary unit classes have been defined and are now available for use. In the next step, the units and equipment modules are assigned to SIMATIC Batch. This is done in the Properties dialog of the relevant folders in the plant hierarchy. We would like to show you a classification based on the example of the Oven unit and its Drain equipment module. The Properties dialog of the Oven folder is opened and the object type of unit is set. The unit type is now Oven. The Drain folder is now specified as an ISA S88 equipment module. All other settings are made in the same way. The batch-related folders are now displayed in green. In the next step, the SFC types that are already created in SIMATIC Manager are defined as Equipment Phases EPH for use in SIMATIC Batch. This assignment is made in the Component view. The Properties dialog of each SFC type is opened and the Category Equipment Phase, or EPH, is set. A further SFC type category that is available for selection is the Equipment Operation, or EOP. This ensures conformity with ISA S88. The difference between the two is that an EOP is linked to a recipe operation in hierarchical recipes, and an EPH is linked to a recipe phase. In general, the scope of an EOP is more extensive and more complex than an EPH. Creating recipes using EPHs allows greater flexibility. EOPs are useful when the equipment functionality is fixed. In the Control Strategy Selection area, you can select the control strategies relevant to SIMATIC Batch. Normally, the setting is All, which is also the default. All the attributes for the objects relevant for SIMATIC Batch are now set. In this section, we will generate the batch type's type descriptions, compile and download the batch process cell data, and compile the system alarm texts in the OS. The first step is to generate the process cell type descriptions. These will be the recipe building blocks. You have already seen this dialog during the definition of unit classes. Generation of the type descriptions is started and completed without errors or warnings. To compile the batch process cell data, the Batch Instances icon is selected and the Compile button pushed. The compilation was completed without errors or warnings. Following compilation, the system messages are now compiled from SIMATIC Batch to the OS. Following this transfer, the last step is to download the batch process cell data to the batch server and client. After checking which data needs to be updated with the download is started by clicking the Start button. The download was completed successfully. Following the download, recipes can be created, tested, and batches created without needing to access the engineering database. This completes all the work necessary in the SIMATIC PCS 7 engineering system. You will now see how users are managed, how a master recipe is graphically created using the equipment phases or EPHs created in the engineering system, and how orders are created and batches started. In the first sequence, stored recipes are read in, and you will then see a brief overview of user management. In the second sequence, a master recipe for producing piccata milanese is developed. In the third sequence, an order to make a batch of piccata milanese will be planned, released for production, and started. In particular, the various options for user control in the Batch Control Center and on the OS are highlighted. In many processes, there is the need to limit the access of each system user to specific functions. A user access management function called SIMATIC Logon is available with SIMATIC Batch that enables you to easily assign the proper system access to each system user. In SIMATIC Batch, this is achieved by defining roles for which specific operator options are enabled and assigning Windows user groups to these roles. In this example, the currently logged on user Mike Bauer is assigned as a member of the Super User group. Mike is also a member of the Windows Logon Administrator group and is therefore authorized to make this assignment. Because Mike Bauer has been assigned to the Super User group, he is now authorized to perform all operations in SIMATIC Batch. The next step is to read in the supplied master recipe database. This is done in the Batch Control Center. The recipe database is stored in the engineering station as an XML file. The XML file format was chosen because it's a text format and will be supported in the foreseeable future. The message that the process cell data needs to be updated is acknowledged. During the master recipe database restore, the user data is overwritten. For this reason, Mike Bauer must be redefined as a batch super user. In a real plant, there are normally more than one user, and each user will be assigned a special role with specific access rights. In this example, we will just define the one user. The process cell is now updated. During the update, the batch data in the engineering system is compared to the data currently in SIMATIC Batch, and if necessary, the data in SIMATIC Batch is updated. The two supplied recipes are sample recipes that will be used in the section From Equipment Phase to Recipe. In this example, the master recipe required to produce piccata milanese will be created in SIMATIC Batch. The master recipe is designed to make 2.9 kilograms or product. The ingredients needed to make this product are oil, pasta, herbs, and tomato sauce. The individual steps involve preparing the water, cooking the pasta, and preparing the sauce at the same time. The dish is completed by mixing the pasta with the sauce. The input materials used in the recipe and the output materials resulting from production, along with any quality characteristics, are now defined. All required input and output materials have now been defined. The next step is to create the master recipe for piccata milanese in SIMATIC Batch. In this example, we will create a hierarchical recipe. With SIMATIC Batch, flat recipes can also be implemented. In this example, the name of the recipe and the name of the product will be kept identical. In keeping with the design of the master recipe, 2.9 kilograms is entered as the reference batch size. To allow the quantity of batches to be scaled, the minimum and maximum batch sizes are also defined. The output material is assigned in the Output Material tab. The editor is started simply by double-clicking on the master recipe that is to be edited in the Batch Control Center. The recipe editor is a typical Windows application with menu bar, toolbar, and status display. Before we start to create the recipe, we will look at some of the important input options available in the Recipe Editor interface relating to hierarchical recipes. These buttons are used to change the view. A recipe can be created entirely using these buttons. We will now show how this is done. After selecting this button, a new recipe unit procedure can be added to the master recipe. This same button can be used to add recipe operations to a recipe unit procedure. Each column in the master recipe procedure represents a recipe unit procedure. The recipe operations are the blocks in the recipe unit procedure. After selecting this button, recipe operations can be created in the form of a reference to library elements. By selecting this button, phases can be added to an ROP. With this button, operator dialogues can be added. The other three buttons are used to add transitions, parallel branches, and conditional branches to a master recipe. Recipe operations are synchronized with this button. Loops are configured with the last button. A previously created recipe structure will be used as the basis for our piccata Milanese product. The left-hand recipe unit procedure is assigned a unit using the preferred unit allocation strategy. The pot 1 unit is assigned to this recipe unit procedure. This is the point at which the integration of SIMATIC batch becomes obvious. All the units and the available equipment phases defined in the engineering system are available in SIMATIC batch for creating master recipes without any additional engineering effort. The preferred unit strategy is the selected method for assigning a unit to the second recipe unit procedure. Pot 3 is then assigned to this recipe unit procedure. The recipe consists of 3 recipe operations that are now named one after the other. Each ROP in a hierarchical recipe contains an ROP sequence. An ROP is opened by double-clicking on it. Each ROP begins with a start step and finishes with an end step. Between these two steps, recipe phases and structure elements such as simultaneous or alternative sequences can be inserted. Recipe phases are inserted by selecting the Recipe Phase button and clicking on the position in the recipe procedure structure where it is to be added. Steps or phases are separated from each other by transitions inserted automatically by the recipe editor. In the first phase, a pot will be filled with 3 liters of water. Because the process is being simulated, the runtime parameter is set to 5 seconds. This value is already set as the default for all phases. A simultaneous sequence is now required so that oil and salt can be added, while at the same time the water is heated to 100 degrees Celsius. In the first phase, 100 milliliters of oil are added. This is followed by 10 grams of salt. In the simultaneous phase, the water is heated to 100 degrees Celsius. The prepare water recipe operation is now complete. The cook pasta recipe operation includes 2 phases. In the first phase, 1.9 kilograms of spaghetti are added. The temperature is then set to 100 degrees Celsius. In the recipe unit procedure, the heat phase is started in the prepare water and cook pasta recipe unit procedures. Here, we could have made good use of the non-self-terminating phase functionality to allow heating to continue uninterrupted between the phases. To avoid unnecessary overheads at the automation level, this was, however, deliberately left out. In the recipe itself, it would have been extremely simple to configure this functionality. We would have simply selected Continue in the first call of the heat phase. The prepare sauce recipe operation is somewhat more involved. We have already seen the input required for a phase. So from now on, we will no longer show each individual parameter setting for the phases. The recipe operation consists of the phases that add 1 liter of tomato sauce, and then heat it to 40 degrees Celsius while being stirred. Finally, 50 grams of salt and 50 grams of pepper are added. The prepare sauce recipe operation is now defined. The recipe is then completed by adding the 2 recipe operations, serve pasta and serve sauce. These recipe operations contain the drain phase. This completes the master recipe. The master recipe is now saved, validated, and released for production. Based on the piccata milanese version 1.0 master recipe, we will now create and start a production batch of 5 kilograms. An order, called Order GS, is created in the GS order category. A batch named Batch 1 for the production of 5 kilograms of piccata milanese will be created in Order GS. And released for production. The control recipe is opened and started. Based on the master recipe, a batch is completed very quickly. Multiple control recipes will be created and started. You will see different batch names in the following sequences. Active recipe operations are indicated in light green. The recipe operation Prepare Water is opened by double-clicking on it. The recipe phases and their states are now displayed. Completed phases are indicated in dark green. Completed recipe operations are also indicated in dark green. Now the recipe operation Prepare Sauce is opened by double-clicking on it. Again, the phases in this recipe operation and their states are now displayed. The batch has completed executing. Before we show you the powerful runtime batch control options available to the operator, we'd like to describe to you the interaction between SIMATIC Batch and PCS 7 OS. You see the control recipe very small in OS runtime. Like before, the two recipe operations, Prepare Water and Prepare Sauce, are opened as soon as they are activated. The batch is started. Pot 1 is allocated. Pot 3 will not be allocated until the recipe operation Prepare Sauce becomes activated. Water is added. Oil is added. Salt is added. The hot plate is switched on. The tomato sauce is stirred. Pepper is added. The unit faceplate displays all the important batch-relevant information. The information displayed includes the batch name, the batch ID, the product, and the master recipe used with its version. If applicable, the name of the formula is also displayed. Since the Pot 3 unit is only allocated when the prepare water recipe operation is completed, there is still no batch information in its faceplate at this time. Pot 3 is now allocated, and the information is now available. The view Phases shows all the existing phases and their states. Now watch the display of the phase status from the control recipe display and from the Pot 1 and Pot 3 unit faceplates. Finally, we want to follow the execution of the phase Add Ingredient in the recipe operation Prepare Water from the OS. The individual alternative sequences are processed according to the recipe. The dialog shown here is identical to the dialog in the PCS7 engineering system and is available on the OS without any additional engineering effort. Once again, this illustrates the benefits of an integrated system. We used the term formula earlier in association with the unit faceplate, but did not expand on it at the time. We will now introduce this concept briefly. A basic master recipe is a combination of recipe procedure and recipe formula. In some processes, several products may have the same recipe procedure and differ in formula. SIMATIC Batch enables you to associate multiple recipe formulas to a single recipe procedure. Each combination of recipe formula and recipe procedure is a new master recipe. This feature saves you time in creating similar master recipes and makes it easy to edit a recipe procedure. This concludes the overview of SIMATIC Batch. This video showed you that the SIMATIC Manager tool is not only used to configure a continuous project, but is also the tool used to configure a batch project. This video also shows you how recipes can be created graphically using the recipe editor and then released for production. You have also seen how a batch is started, how the execution of the control recipe is displayed in the Batch Control Center, and how an operator can monitor and control an active batch using the powerful tools provided by SIMATIC Batch and PCS7. As always, the operator has the option to manually intervene in the process with simple commands that require acknowledgement. Tools are provided with SIMATIC Batch that enable the operator to hold a batch, pause a batch, resume a batch, and to abort a batch. If you would like to get a more detailed understanding of the technical options and modes of operation available with SIMATIC Batch, we recommend that you watch the third part of this CD, From Equipment Phase to Recipe, that shows you how to create new equipment phases, how to use them in recipes, and how to control and monitor them on the OS at runtime. In this illustration, the units in the unit class POTS will have an equipment phase called Ventilate added to them. The Ventilate equipment phase opens a ventilation valve for a specified time if a batch is held or aborted. This same phase will be used in all three units, Pot 1, 2, and 3. This is a scenario where using SFC-type templates will save you implementation time. To implement this equipment phase, you will create an SFC type. To this SFC type, you will create a control strategy called ventilate. You will then create a recipe parameter called T-length that represents the duration the ventilation valve for a pot will remain open when the ventilate phase executes. In this example, the ventilation phase ventilation valve is called V1. The ventilation valve is represented by a block contact. The ventilate SFC type is created in the SIMATIC Manager component view and opened with the SFC type editor. In the characteristics dialog, the control strategy, the set point, the timer, and the block contact are specified. The control strategy is defined, for example, by selecting Control Strategy and entering a name for the control strategy. The number 1 is generated automatically and can be queried in the start conditions to start the control strategy. The set point, the timer, and the block contact are created. 2 required sequences, run and hold abort complete, are developed. The sequences to be executed are straightforward. The main sequence of the SFC type is the run sequence. In this sequence, after the start command, the ventilation valve is set to auto mode. The valve is then opened. At the same time, the timer is set to the selected recipe parameter duration setpoint and started. The next transition tests whether or not the valve has actually opened and whether or not the timer has started. Another transition monitors the expiry of the timer. As soon as the timer has expired, the valve is closed in the next step, and the valve closure is then confirmed. The final step in the sequence terminates the timer in all situations, even if the sequence ends abnormally. The hold abort complete sequence closes the valve automatically if the batch is completed normally, is held, or is aborted. The conditions for the start of a sequence are specified in the Start Conditions menu. To classify the SFC type as an equipment phase, the batch category EPH, or equipment phase, is selected. The phase is then available later in the recipe editor and batch control center. The new equipment phase can now be inserted in units and interconnected with actual valves. Creating the sequence would have been necessary in any case to control the valve. The extra effort involved in creating an SFC type as opposed to a normal SFC is more than compensated by the ability to make central modifications and the ability of creating instances of the SFC type. Note that there was no additional SIMATIC batch engineering involved when the ventilate SFC type was created. The created equipment phase must now be linked to the Pot 1 unit. In addition to the existing phases, a new equipment module folder with the name Ventilate must first be created in the plant view in the unit folder. A CFC chart called Ventilate Pot 1 is then added to this folder. This chart will contain an instance of the Ventilate SFC type. A second CFC chart, called Pot 1 Valve, is also created in a subfolder called Val Ventilate. The valve used to ventilate Pot 1 is configured here. A valve block is inserted in the pot 1 valve chart in the CFC editor. The valve block is given the name P1V1. To simulate signals from the valve block, the Q control output is interconnected with the FB open input and negated with FB close. An instance of the SFC type is now created for pot 1, and a connection established between it and the valve block that was just inserted. In the CFC editor catalog, our SFC type appears in the Other Blocks category. This block is placed in the Ventilate Pot 1 CFC chart and given the name T1 Ventilate. The interface parameters used in SIMATIC batch were changed to be visible. Establishing connections between the two blocks is extremely easy in the CFC editor. Both charts are opened in the CFC editor and arranged beside each other. After selecting the input and output in the blocks, the CFC editor creates all the relevant interconnections to the valve automatically. To make sure that all the batch-relevant information written to Ventilate Pot 1 by SIMATIC batch can be passed onto the valve, the batch-relevant outputs are also interconnected with the valve. To ensure that the actual process value at the duration set point is displayed correctly in the OS faceplate and is also available for SIMATIC batch, a connection must be established between the output of the current timer value and the process value input. The Pot 1 equipment module folder that represents Ventilate is now copied to Pot 2 and Pot 3 and modified to point at the ventilation valve for Pot 2 and Pot 3. All names of the folders, charts, and function blocks need to be adjusted. The charts are compiled, and the data is then downloaded to the automation system. Prior to compilation, a further instance of the phase should be created, or this should at least be pointed out, so that the type instance concept is clearly highlighted. The program is downloaded in the controller. Now the changes to the OS are compiled. Before the OS server can be downloaded, several steps must be made to accommodate SIMATIC batch. In the configuration dialog for SIMATIC batch, the batch types are generated. This makes the ventilate phase available to batch. We then compile the batch instances and then download the process cell data to batch. So far, the new equipment phase has been created, and the blocks used have been inserted and interconnected with the pot ventilation valves. Changes are still needed to operation of the process cell, and recipes still need to be created. To be able to monitor the new phase on the OS, an entry must be made to the OS faceplate. The modifications are made in the kitchen.pdl file with the graphics designer. After opening the Properties dialog of the Pot 1 unit block icon, the Pot 1 unit is selected first in the configuration box. The T1 ventilate phase we created can then be inserted into the configuration by double-clicking. The PCS7 OS runtime name is modified automatically, but it is renamed as Pot 1. The picture is stored, and the WinCC Explorer is closed. The block icons for Pot 2 and Pot 3 are modified in the same way. Now the OS server is downloaded online. The process does not need to be taken offline to do this. The download is successful. With this, the engineering on the engineering station is completed. The following engineering is done on the OS and SIMATIC batch client respectively. After starting the batch control center, the user is informed that the process cell data needs to be updated. The process cell is updated. The newly created phase is used in the supplied master recipe, template recipe getting started V1.0. The modified recipe is stored under the name Recipe Ventilate. In the recipe editor, the newly configured ventilate phase is inserted in the recipe operation Cook Pasta. Because we defined the SFC type as an EPH or equipment phase, it is now included in the phase selection menu. The ventilate control strategy we defined can also be used elsewhere. In the Parameters submenu, we can now enter a time value in seconds for the duration the ventilation valve is to remain open when the ventilation phase runs. After saving the master recipe, it is put through a validation check and is found to be OK. Finally, we can release the finished recipe for production. A batch is created with the new recipe in the Orders folder. Released and started. The newly created recipe phase has been used successfully in an existing master recipe with very little effort. In this section, you have seen how a new equipment phase can be developed in the SIMATIC Manager as an SFC type. At this point, we should mention that equipment phases can also be implemented using batch interface blocks, although we will not expand on this here. You have seen how a recipe phase created in this way can be included simply and intuitively in a master recipe. The parameters specified in the SIMATIC Manager, such as set points, appear in SIMATIC Batch as recipe parameters, and the required values can be entered there. The procedure as shown here is only possible because of the tight integration of SIMATIC Batch with the modern SIMATIC PCS 7 process control system. Thank you for viewing this video. For more information on PCS 7 and SIMATIC Batch, please contact your local Siemens representative.